Bueno, buenas tardes a todos. Bienvenidos a la última edición por este semestre de los Coloquios IB. Hoy tenemos el agrado de presentarles a Anthony C., que es invitado del programa Maldacena. Así que bueno, acá la presentación formal de Anthony la hará Gonzalo. Bueno, muchas gracias.
Bueno, muchas gracias por la invitación. Y bueno, ahora vamos a cambiar en inglés, así que voy a hacer la presentación en inglés también. So today we are very pleased to have Professor Anthony C. visiting from the Kavli Institute for Theoretical Physics at the University of California. And as Julian said, he's a visiting professor from the Maldacena program. So I just wanted to say regarding this program that it was created from a generous donation of Juan Maldacena, and it has just turned 10 years. And in these 10 years, it has allowed us to bring many leading scientists from different research areas, ranging all the way from mechanical engineering to condensed matter and high energy physics. So it has been really helpful for the Institute. And Professor C visit is also special because he's the first invited professor in the program who was directly proposed by students. And one of the reasons why he was proposed by students is because of his committed work towards teaching physics. And this work has been reflected in 3 books, in quantum field theory, general relativity, and group theory that have become standards in the field. He also has many fundamental contributions in physics, but I prefer not to enumerate them, and instead, let's just go to the colloquium. So let's hear about his talk on quantum field theory. Thank you.
Thank you so much, Professor Toroba. I'm very honored and pleased to be in San Carlos de Bariloche today. And this is my first trip to Argentina. And I grew up in Brazil, and so I've always wanted to visit Argentina. But for some strange reason, everybody in my family has visited Argentina many times, but not I. The other reason that I'm particularly close to Argentina is that you know that American universities have this silly custom of every university has some mascot, some crazy figure that runs around on the sports teams and so on. And UCSB's mascot is the gaucho. So we all know about the gaucho. So today I'd like to talk to you about quantum field theory. It's arguably the greatest monument to the human intellect. In any case, it's the most accurately tested physics in physics. Most people think the most accurately tested theory would be Newtonian mechanics or something like this, but no. It took us a long time for when human beings first realized that nature, their laws governing the universe, it took a couple of millennia before we realized that this entire universe is pervaded with quantum fields and that we are surrounded by quantum fields. So let me begin by asking 2 questions. What is quantum field theory and who needs quantum field theory? And this is in quotes. And the answer to the second question is very simple. And these days, one doesn't even need to know quantum mechanics to be a professor of theoretical physics. Well, I emphasize that I don't speak of experimental physicists for whom I have only admiration since they can do things I cannot even dream of doing. But when I was a student, I could not have imagined that you don't need to know quantum mechanics to be a professor of physics. But now our physics department is, in fact, has a number of people in this. So the other question is, what is quantum field theory? So chapter 1.1 of my textbook on quantum field theory says that quantum field theory arose out of our needs to describe the ephemeral nature of life. And life is, as according to some saying, it's like clouds and smoke passing in front of our eyes. It's very transient. But no, more seriously, quantum field theory is needed when we confront simultaneously the two great physics innovations of the last century of the previous millennium, namely special relativity and quantum mechanics. It's when you combine these two that you have a totally new set of phenomena. So let me draw what I call the square of physics. The square of physics, these lines are just to guide the eye. I mean, they're not sharp division. So if we have very big things moving very slowly, then we have classical physics. If we have the big things moving fast, then we have, for example, rocket ship traveling through near light speed. There is no need for quantum mechanics. But for small things, you need quantum mechanics. For even very slow things, for example, slow-moving electron in the hydrogen atom, there is no need for special relativity. So it's really in the peculiar confluence of special relativity and quantum mechanics, a new set of phenomena arises. Particles can be born and particles can die. So this is what I mean by quantum field theory is necessary to describe the ephemeral nature of the world. So it's a new subject of physics, quantum field theory, is needed to describe birth and death and some kind of life in between. So I keep forgetting this. Okay, so two gold-plated equations of physics. Okay, so first, of course, we know quantum mechanics, the gold-plated equation is uncertainty principle. The uncertainty in energy is 1 divided by the uncertainty in time. So this means that accounting errors could be tolerated for a very short time. And special relativity, on the other hand, tells us that energy is matter, is equal to matter, equal to mc squared. These are the two famous equations of physics. And this tells us that accounting errors could be turned into stuff, into actual matter that you can use. So if you have only quantum mechanics, nothing much happens. There are accounting errors, but only for a short time, then it goes away, just fluctuation. If you only have special relativity, there's also nothing happens because energy there is no energy fluctuation. But when you combine these two, you see that there's a whole new set of physics. So we need both. I like to emphasize that we need both quantum physics and special relativity. Then particles could pop out of the vacuum and pop back into the vacuum. It could happen in two cases. If anybody can think of a third case, that would be extremely great. So we know of two cases in which this could happen. One is if there's energy available, for example, in cosmic rays or in an accelerator, there's energy available. Or another case is when you're near, that's what, for a long time, people thought this was the only case possible. But then Hawking came along and pointed out that it's also possible near a black hole horizon because you can eliminate one of the particles. So in contrast, in non-relativistic physics, no matter how you shake and bake the Schrödinger equation, you can always the same number of particles. If you start with 7 electrons with a Schrödinger equation, then no matter how hard you work on the Schrödinger equation, you always have 7 electrons. There can be no more, no less. So we need quantum field theory. So I'll now describe how the concept of field arises. So the easiest way perhaps to understand what a field is to consider a matrix, which is, in the simplest, for this talk, I'll just say that it consists of a lot of mass points connected by springs, but very far away on distance scales much, much larger than the lattice spacing. This looks like a continuous field, right? It looks like a membrane of some continuous object. And you can form wave packets of the normal modes. They're normal modes vibrating waves, and if you can form wave packets. And the anharmonicity in the spring will cause them to scatter and decay. So this looks very much like what we observe in nature. So from fields, we easily go to the concept of particle. So an excitation in the field is a particle. And so if I plot in space-time, let's say this is space, this is time, then we could have a source in which it produces an excitation in the field and could propagate to another place, which we would call the detector, and a particle is then detected. So the next thing is from particle to force. Once we have particles, then we can produce a force. And this cartoon describes a marriage broker in many ancient culture, like in China or Jewish culture. There is some marriage broker, which is typically a rather heavyweight lady who goes between different families. But the interesting, for our analogy, the interesting thing to note is that how far she can travel is limited by her weight. So the range in which you can go from one family is limited by her mass. So this is an analogy I invented, which is taken from my popular book, Field for Symmetry. Now, how did I end up writing a popular book when I want to talk about quantum field theory? Well, there's a story. I was sitting in Weinberg's office, and I told him that I wanted to write a book on quantum field theory, a textbook. And Weinberg, this was 1984, so that's more than almost 40 years ago. He said, no, people write textbooks without knowing how to explain things. Before you write a textbook, you must write a popular book. Because if you can prove that you can explain things to the person in the street, then you can explain things to the physics students. So that's how I published this book, Field for Symmetry, which has been around for a while. Now, after this book came out, it was translated into German, into Spanish, into Chinese, into Japanese, Korean, and so on. And I always wanted the book to be translated into French because I could read French, but I had to wait 34 years before a French translation finally came out. And interestingly, it was only after I've lived in Paris for a year. Then because I have an address in Paris, and then the publishers in Paris, they realized this person is a serious person because he lives in Paris. So here's the French book. And when the French translation came out, then last year, almost 40 years after my book, a Turkish translation was published. And in the United States, it's been published by two publishers. First by the commercial publisher Macmillan, and then Princeton University Press bought the rights from them, and they've published several editions. So in particular, this edition is the US in 2007 edition, and I was very pleased that Roger Penrose liked my book, and he wrote a foreword. This book has a foreword by Roger Penrose. So it was, but for this audience in Argentina, I want to especially show the Spanish translation. It was published in Barcelona, and it is, interestingly, it's the first translation that does not have a tiger on the cover. And it's, of course, in Spain, the Moorish Spanish architecture has a lot of symmetry properties. And in many countries, the translation in my book, for example, in China and Japan, they always have some difficulty with the title because they don't understand the association with the tiger. And so, for example, in France, the translator they translated, it comes from a poem by Blake. So now let me see. This is, okay. The Germans, then after I wrote this book, the Germans invited me to India, and but it's not connected to physics. It's just that they wanted somebody to talk about symmetry. So the trip was financed by the State Department, and I gave this talk in Mumbai. And so it has helped my career a great deal because some English professor, University of Virginia, who was the editor of a literary magazine in the United States, he really liked this, my talk. So he published it in this journal, which is a serious English journal. And here's the newspaper reporting. Now, the amusing thing, let's see, I guess okay, so so now I come back to the physics. From particles to force. Now, ever since the first day that we studied physics, we were told about forces. For example, the electric force, the magnetic force, and so on. And if we ask the physics professor where does the force come from, typically, a professor cannot answer that question. So since the early days of physics, the notion of force has been among the most basic and the most mysterious. Where do forces come from? So it was with considerable satisfaction that physicists finally understood the origin of force as being due to the quantum exchange of a particle. So now, for example, we know that the electric force is due to the exchange of photons, and it's the quantum exchange of a particle that generates this force. So it took physics really several hundred years before we understood this. And now, given this understanding, in 1934, Yukawa, the Japanese physicist Yukawa, described that a marriage broker, as I showed in my earlier, must be provided for the strong interaction as well, the force between the proton and the neutron, between two protons. And we, after so many decades and so on, we forgot how much courage it took. I mean, at that time, it took a tremendous amount of courage to hypothesize a new particle, which became known later as the pi meson, or the pion for short. So, strikingly enough, he was able to predict the properties of the pion. And the reason he was able to predict the properties of the pion is because he knew the range of the strong interaction. And so, as I described in my analogy, the mass of the marriage broker is limited by the distance the marriage broker could travel. So this was extremely striking, not only to predict a new particle, but he was able, for example, to say what the mass of this particle was. So for that, he was awarded the Nobel Prize. So from particles to force. So another rough analogy, which a lot of people like, given our previous simple analogy of a mattress being a field, if you introduce two external lumps on a mattress, they attract due to the distortion of the field. So all this is described in great details in my various books. So, as you know, the physical world results them from a web of interactions. Some of them are attractive and some are repulsive. And quantum field theory answers why. So again, when we were studying physics, or when we were undergraduates, The professors just tell us the electric force between two like objects are repulsive and the gravitational force is attractive. And why? We just take this accept this as a fact. But the sign, whether it's plus or minus, whether it's attraction or repulsion between like objects, it turns out in quantum field theory to depends on whether the spin of the mediating particle is odd or even. And so this fact ultimately could be traced to the difference between time and space. So those of you who study special relativity know that there's a minus sign between time and space. So ultimately, that's where it comes from. So this web of attraction produced a web of interactions, produced a very interesting universe for us to live in. So if you exchange a spin zero particle, you produce this attraction, and that's the strong nuclear force of Yukawa, protons and neutrons coming together. And if you exchange a spin one particle, for example, the photon, you get a repulsion. And if you exchange a spin two particle, you get an attraction, for example, the gravity. So now we can give given this fact, we can give a lightning history of the universe in one transparency. So the universal gravitational attraction due to the spin two particle produces the instability that drives the formation of structure in the early universe. Dense regions become denser still. And this is completely analogous to the rich becoming richer. So the region in the universe that's dense, they attract other stuff surrounding them, and they become even denser. So you can calculate that this is the rate at which this happens. And there's you can also think of meanwhile, the photons and neutrinos, because they don't interact, they tend to take away, they tend to smooth things out. And so they act as a kind of taxation. Now, meanwhile, the attraction between the protons, due to the spin zero particle, ignites the stars. When a lot of protons are together, they form stars, they start nuclear reactions, and they eventually form the rich variety of nuclei. Now, the attraction between positively charged nuclei and negatively charged electrons, due to the spin one particle, produces the atoms. And so this is a one-page summary of the history of the universe. Now, we have this concept of field, which goes back to Faraday. Faraday is a very interesting character because he came from an extremely poor background, almost Dickensian, like as described by the novels of Charles Dickens. He didn't really have an education. He worked for a bookbinder. And so the mathematics of the time of the continental philosophers, by that he was referring to the French guys, people like Ampere and so on, who write down partial differential equations are completely beyond him. So he was compelled to invent his own pictorial language, right? So that is absolutely amazing that he just drew some pictures and called it a field. And now the field has become the most important, most basic concept in theoretical physics. Well, here's just a side remark from my book about basic versus applied research. Because at that time, this is only for, presumably there's nobody in the audience who is in charge of giving out money. So in the US, of course, the analog is the military wants to fund a lot of research. And at that time, of the time of Faraday, they want faster, Royal Navy want faster communication. And then there are these people in the basement, like Faraday, messing around with wires and frogs and so on. I mean, do you give money to these people or give money to those people trying to breed stronger pigeons? Of course you give money to the people with the stronger pigeons. So Maxwell's theory of the electromagnetic field contains two hidden symmetries that will rock 20th century physics. They were hidden in the 19th century. One is, of course, special relativity. It's Lorentz invariant. And the other is gauge invariance. So it's remarkable in hindsight that the theory would contain two important symmetries, and yet nobody noticed in the 19th century. So an interesting question, I think, is it conceivable that present-day theory also contains hidden structure? So, for example, now, Yang-Mills theory, in some sense, also terrible notation, because it's really a redundancy in description. In a non-abelian gauge theory, you introduce a lot of stuff that are not physical, which are called gauge degrees of freedom. So this twistor formalism that some people are now working on, perhaps the first step in fixing this, in avoiding introducing redundant degrees of freedom. So if you go back and look at Maxwell's paper, you ask, how do these very smart people like Maxwell, how did they miss seeing these two symmetries? And the answer is, of course, terrible notation. So that's at least in hindsight, the terrible notation. So this I always ask the student. I know the students here are having an exam on electromagnetism. But when I teach electromagnetism, I always ask the students, why is the magnetic field H? And if a student can answer this question, I give him an A, him or her an A. And so in my experience, I have not taught electromagnetism very often, but I have never encountered a student who could tell me that. Does anybody know the answer in the audience? So this has to do with the terrible notation. So, of course, Maxwell did not have a vector notation, and he wrote out every component. So the electric field is obviously E, starts with E, but then there are two other components. So the three components of electric field is E, F, G, and then magnetic field is H, I, J. So it's just, by the way, the vector notation was very slow in being adopted by physicists. If you look at Einstein's paper on special relativity, it's absolutely amazing when I read them. He doesn't use vector notation. And we would use coordinates, and the different observers, we just say X and X prime. But he actually writes out all four components and so on and so forth. He doesn't use vector notation at all. So already in non-relativistic quantum mechanics, the photon, which is the electromagnetic field, it's kind of a strange, so in a course on non-relativistic quantum mechanics, towards the end of the course, we talk about radiation from atoms and so on. That's what we teach students. And from an atom from an excited state to it jumps down from one orbit to the other orbit, emitting a photon. But this is what Americans would call a half-assed treatment, okay? So recently my book is being translated into Chinese, and so it was interesting how they would translate this into different languages. So in this treatment that we give to students, the electromagnetic field is treated as a field, but not the electron. So obviously this is completely strange, that one particle is treated as a particle and the other as a field. So this is what led Jordan, Heisenberg, Dirac, and so on to introduce a field to describe the electron also, just to be balanced. And I just got an email from some historian who told me Jordan was probably the first one. Now, Fermi had this important idea when he wrote down the weak interaction. So when he wrote down the weak interaction, people did not believe that particles can be created. But Fermi said the photons can be, if the photon can be created, the electron can also be created. So all particles since then are just excitation in some field, okay? So including the graviton. The graviton is just a particle like any other, an excitation in the gravitational field. So for example, this is emphasized in Weinberg's textbook on gravity. He said he doesn't like to talk about Einstein geometry, curvature, and all these things. And he treats the gravitational field just due to a spin 2 particle. But this is somewhat mysterious because this excitation, this graviton, you may treat it like any other particle, but somehow it's also responsible for the space-time arena in which all the fields work and play. So I think the central mystery, as Professor Toroba can explain to you more than I can, is that the question is whether gravity is somehow different. How do you have quantized gravity, whether you even need to quantize gravity? And then, of course, the big paradox of the cosmological constant. So with gravity, the square physics that I described earlier become a cube of physics. It has now become, there's a vertical dimension in which you turn on gravity. And Newton already climbed up on the first vertex. And so we are now trying to climb up on the most difficult one, in which we have special relativity, we have quantum mechanics, and we have gravity, all three. Okay. But in this talk, I'm just going to concentrate on the square. Okay, so after talk, as you can see, I noticed that this is exactly 20 years since I published this book. My quantum field theory book was published in 2003. So this was also almost 20 years after talking to Weinberg, who told me to write all these popular books. So I published my quantum field theory book, and then this is the cover. I'm very particular about the covers of my books. So my idea is that here's the student who's trying to reach field theory, and first has to cut through all this to get to the field. And interestingly, various famous physicists asked me where this painting comes from. In fact, I got an email from 't Hooft, who was almost sure that this is a Dutch painting. And so it turns out it's not a Dutch painting, it's a French painting. So 7 years later, there's a revised edition that was published. And now has been translated into a Russian and later into Japanese, but only volume 1. They divided into 2 volumes. And my Russian physicist friend, when they come to my office and they see this book, they said this is, my book has a logically inconsistent title because Russia being a very cold country in the old days, they did not have nuts. It's too cold to grow nuts. So in a nutshell, means nothing to them. So the Russian publisher translated into quantum field theory in 2 words. And so the title already more than 2 words. So it's also, last year was translated into Chinese. And so the rise, one of the things that I emphasize in my book is the rise of field theory in condensed matter physics. So when I was a graduate student, condensed matter physics did not use quantum field theory at all. The old-fashioned solid-state physics, of course, was based on band structures and so on. And when I was a student, when I was a student, there were textbooks by Feller and Wolotchka and by Abrikosov et al. These 2 books. They apply field theory to condensed matter physics, but it's perturbative field theory using Feynman diagrams. And, but later, the exciting development, I think, in condensed matter physics was quantum Hall fluid. It turns out the microscopic degrees of freedom, which of course electrons, but the long-distance physics is described by Chern-Simons gauge field with fractionally charged excitation. So this shows the power of quantum field theory that from electrons you can get some non-trivial gauge fields with fractional charge excitation. So since then, quantum field theory has been applied to condensed matter physics in many different areas. And the other thing in my book is that when I was a graduate student, gravity was completely ignored in the courses, right? The kind of textbook I had when I was a student, for example, Bjorkin and Drell, did not mention gravity at all. There was no such thing as gravity. And so when I wrote this book, I told Weinberg that I was going to write this book, and I wanted to, so mentally, I thought of Peskin's book in one side and Weinberg's book on the other side, and I want it to be, to make myself as far away from them as possible. So in many ways, I tried to write a book that was completely different. Now, quantum field theory has had two near-death experiences. It almost died as a field. So once was in the late 1940s because it was unable to produce Lorentz covariant results. And it was also divergent. So there's still some old-fashioned people and some old-fashioned books talking about divergence. When I was in graduate school, Coleman and others emphasized to me, Schwinger and so on, there's no such thing as divergence and infinity. It's only cutoff dependent. Some quantities are cutoff dependent, some quantities are not. So in the 1940s, as you all know, very interestingly, it's the young people who are the revolutionary conservatives. People like Niels Bohr and Oppenheimer and people like that want to give up quantum field theory, especially Niels Bohr, want to invent something new. But interestingly, it's the young people, the old people that want to throw everything away. Sorry, the younger generation like Feynman and Schwinger and so on, that try to fix quantum field theory. Another near-death experience was, of course, in the late 1960s. It's the inability to deal with the strong interaction. So this led to the S-matrix school. So when I was a first-year student at Princeton, a freshman, another undergraduate came to me very excited, and he showed me a very thin book on S-matrix theory. There are almost no equations, and because everything is determined by S-matrix. And he told me that we don't have to, it's wonderful now, we don't have to waste time learning nonsense like quantum field theory, and we just learn S-matrix theory. So the US, the younger people here probably don't know the history. At least in the US, physics sort of split between the East Coast and the West Coast, and the West Coast being the S-matrix. And I was very fortunate to be on the East Coast where people still believe in quantum field theory. So when quantum field theory triumphed, Sadie Coleman described this as a victory parade that made the spectators gasp with awe and laugh with joy. And so, okay, so now let's talk about a little bit about the formulation of quantum field theory. When we teach or learn quantum mechanics, typically we learn the Schrödinger or Heisenberg formalism. And conceptually, there's a more profound formalism, which many students are not taught, and which leads naturally to quantum field theory. And this is the Dirac-Feynman path integral, or the Schwinger functional integral formalism. So let's go back to the basic two-slit experiment in quantum mechanics. There's a source that emits particles that are detected on a screen, and there's an amplitude for the particle that goes through this slit, and an amplitude goes through that slit, so you add the two amplitudes. Now, I'm sure those of you who have taught students, at least from my experience, if you teach students this, students never ask, almost never ask, what if there's three holes? So, suppose you have three holes, and so the professor would just say you add all these amplitudes. And suppose you put in another screen and put in some holes. And the professor said, you just add all the amplitudes. But now somebody like Feynman came along and said, what if you put in a screen and you put in infinite number of holes so the screen disappears, and you put in infinite number of screens? And in some sense, this is the most Zen of all. You add infinite number of screens, and then you drill infinite number of holes in each screen so that everything disappears. So you have to add the amplitudes over all paths, okay? And so it becomes an integral over all paths. And that's the Dirac-Feynman path integral formalism. Now, so in my book, I have this cartoon. Physics students learning the path integral formalism contemplates the different paths you can form in life. So this is typical of many students at my university. But of course, the big difference is that we don't know what we are supposed to minimize, and we don't know when the path would end. So in some sense, quantum field theory just is one great big fancy sum or integral. Okay, so you have an integral over an exponential of some function. And the field phi is then a function of x and t, where x is space as d-dimensional, capital D, and there's always one time. And now we can see the relationship between quantum field theory and quantum mechanics. It goes down to quantum mechanics. If you don't have space, you get rid of space, and then you only have phi of t, okay? So then you call it Q. So Q is actually the position of the particles in the usual elementary formulation. So you see that quantum mechanics that we taught to students, just 0 one-dimensional field theory. And you can go down one more step, and you don't have any time at all. And this is just 0 plus 0-dimensional field theory. But you let phi be a matrix. So then this is still non-trivial. You have to integrate over a matrix. And this is called random matrix theory, which I have worked on. And it's very interesting theory. And finally, as we said, we go down one more step. If this is not a matrix, but just an ordinary variable, then this is just an ordinary integral in calculus. So in some sense, I'm exaggerating somewhat. With some exaggeration, you can say the 100 years of quantum field theory, I guess what I wrote here was 80 years, but now it's almost 100 years since I wrote the book. 100 years of quantum field theory is people finding different methods or tricks to do this integral. You could say that. So for example, lattice gauge theory, people replace this integral by a sum, and then they use the computer to do the sum. Okay. So in a sense, all of the history of quantum field theory in the last 100 years has been finding tricks. Now, the simplest example you can imagine, if you're asked to do an integral like this, and I think most people in the audience can realize that this integral cannot be done exactly, cannot be done analytically. But one way to do this integral is, of course, to expand the phi 4 that you cannot do, that the phi 4 expand this exponential phi 4 in an infinite series, just the exponential series, then this is just a Gaussian integral. So you can do this term by term. This is really one of the most fabulous ideas in the history of physics. You take something you cannot do and expand it into. By the way, I emphasize to students that some of the most fabulous ideas in physics and in mathematics are always incredibly simple. Like when I've been teaching group theory, and I told that Lee's algebra, Lee's idea that made him immortalized is to just say you study a group, you study only near the identity, and that's enough. And similarly, this is really one of the most important ideas of physics. And then you draw little diagrams to keep track of the terms. There are many, many terms. Now, of course, for actual field theory, this is more complicated. So when I was a student, I was really eager to learn about Feynman diagrams, which I had heard so much about. Everybody had talked about Feynman diagrams. But then when I learned it, I realized it's just this trick. And you draw little pictures to keep track of all the terms. So here's Feynman's, as you know, his last blackboard. It's interesting. He sets impossible standards for himself, as you can see in the upper box. But also notice that to learn, he has a list of things he wants to learn. And one of them was crossed out. So Schwinger, on the other hand, in 1948, he calculated the first term of the anomalous magnetic moment of the electron. Okay, so this is Dirac had calculated the magnetic moment of the electron from his equation, and Schwinger in 1948 was able to calculate deviation from Dirac's value. So they were in a race, Feynman and Schwinger was very proud that he beat Feynman, and Feynman acknowledged that he was not able to do the calculation. So if you ever go to Cambridge, Massachusetts, you should go visit the cemetery, and here's Schwinger's tombstone. And on his tombstone, he wrote down the answer, alpha over 2 pi. Okay. This is also perhaps an interesting story. And his wife is named Clarice. So recently, a young physicist had a baby girl, and he asked me, he said, could you suggest some good names for my baby girl? And I was writing this book, and I said, Schwinger's wife is named Clarice. So this physicist named his daughter Clarice. So the current value for the anomalous magnetic moment of the electron is, experimentalists have measured this to some fantastic degree of accuracy and precision, right? So what did Schwinger got? Schwinger got the 116. And now, of course, people have calculated all of this. And so to put the agreement between theory and experiment in rough pictorial perspective so we can have an idea, as I said in the beginning of this lecture, quantum field theory is the most accurately tested theory in physics. To see how amazing this agreement is, try to visualize the distance between Bariloche and Valdivia. So I looked on the map. It's 350 kilometers by car. Then the present uncertainty in this between theory and experiment, between the quantum field theory calculation and experimental value, corresponds approximately to 1.3 times 10 to the minus 2 millimeter. That's absolutely amazing. So just so that you know what 10 to the minus 2 millimeter is, a width of a human hair ranges from this value to about 10 times thinner. So it depends on how thick your hair is, what the texture of your hair is. So there is no argument that the people that continue Schwinger's calculation did a fantastic job in getting agreement between theory and experiment. So this is from my quantum field theory book about, again, Schwinger's triumph over Feynman. It turns out that these are the Feynman diagrams you have to calculate, and it turns out there's only one Feynman diagram you can calculate. So now Schwinger's triumph is almost half a page, only if you argue, it's 1 page in a textbook. Okay? It's a trivial homework problem for a student. It's amazing how physics made tremendous progress this way. Schwinger was fond of saying that Feynman brought quantum field theory to the masses. So, of course, you probably know Schwinger and Feynman, why they have great respect for each other. They were very competitive with each other. And Schwinger always thought that by inventing Feynman diagrams, everybody could be a quantum field theorist. And it is true. One of my colleagues referred to some people as professors of Feynman diagrams. People he doesn't like, he would say, oh, he's a professor of Feynman diagrams. So Schwinger was very upset So I was a graduate student at Harvard. I took Schwinger's field theory course, and that's how I learned quantum field theory. But Schwinger did not allow anybody to use Feynman diagram. He never taught Feynman diagrams. So if you want to learn Feynman diagram, we have to learn our own. So, and this is described better than me by Paul Martin. Those of you who do the condensed matter theory, I'm sure you heard of Martin. He was, of course, much older than I was, and than I am. And he recently passed away, in fact, I think. He described in his generation a dark recess, the sub-basement of Lyman. Lyman is the name of the building of the physics department, where theoretical students retired to decipher the tablets and where the ritual taboo on pagan pictures could be safely ignored. So this is the pagan pictures, the Feynman diagrams, and it's completely taboo. So Schwinger had many graduate students at that time. I was very fortunate again. Various people advised me not to study with him. And so some of these students are my friends. And when Schwinger gave them a calculation to do, they would go home and hide somewhere. And then they would do the calculation using Feynman diagram. And after they obtain the result, they translate everything back to Schwinger's language and then show it to Schwinger. But Schwinger is an extremely nice person. The two of them have such different personalities. Of course, I have the greatest respect for both of them. But you can see they have totally different personalities. And here, an expert on, this is a picture after the Nobel ceremony in Stockholm. This is Schwinger and Feynman. An expert on body language would have a wonderful time analyzing this photograph. And this is so typical. Feynman would be talking away, waving his hand. And you can see Schwinger. He even has white gloves still. And he's trying to get away from him as far as possible. Just sort of get away from this guy. Stanley Desser, whom some of you probably know, who unfortunately passed away a few months ago, he wrote a very interesting article that says, analyze these two persons, personalities and so on, background. And it is remarkable that they have exactly the same background. They're both middle-class Jewish Americans from New York City, but they have totally different personalities. And I like both of them. And I like both of them, and they seem not to dislike me, at least I could say that. But totally different. Feynman likes to go to nightclubs and so on. So if he invites you to go to a nightclub, that's one of the triumphs of your career. And Schwinger is exactly the opposite. I cannot imagine something like that. So here are some of the landmarks of quantum field theory. First, internal space was introduced by Heisenberg with isospin, and gauge symmetry was introduced by Weil, and this was generalized to non-abelian gauge theory by Yang-Mills and other people, and so on. And I wrote a simple introduction for undergraduates to some topics in quantum field theory in part 9 of this book. So this is a course I teach at UC Santa Barbara, which is called Fly-by-Night Physics. It's a special topics course I invented to help develop physical intuition. And the chair of the physics department now wants this to be a regular course. So this was published by Princeton University Press 3 years ago. And it's how to do back-of-the-envelope calculation, how to guess the answer, and so on. So in this book, I have some undergraduates who want to learn quantum field theory. There's a very simple discussion in this book. So let's now go back in history. So the influence of Feynman diagrams, of course, was overwhelming on quantum field theory for many years. And in fact, when I was a grad student, some people even say, and I don't know if there are people here old enough to remember this, there are people who say quantum field theory is equal to the sum of all Feynman diagrams, and that's it. So again, it took some young people, two brilliant guys, Tuhoft and Polikov in the 1970s, and I described them as breaking the shackles of Feynman diagrams. So everything was tied down by Feynman diagrams, but then they discover a phenomenon in quantum field theory that goes like e to the minus 1 over g squared, where g squared is the coupling constant that I introduced before. So remember when we did Feynman diagram, it was taking the integrand and expanding it in a power series in G. And this obviously cannot be expanded in power series in G. So, so from that point on, we have finally broke away from Feynman diagrams. And there are all many things that can be derived that can never be seen by Feynman diagrams, such as all these topology and so on. So I then, Princeton University Press asked me to write a popular book based on my lecture, this lecture which I've given many places around the world, I guess in 20 years after my book is published. But they want me to write a book at a lower level for the general public. So this book just came out. So I'm almost finished in case you're getting impatient. So I'd like to ask the audience, what is the purpose of studying physics? Okay, so what is the purpose? So in the United States, when you give this talk, maybe some students in the audience would jump up and say it's to make as much money as possible. Well, that's of course a very stupid thing to say, because then you should not be studying physics. There's a much easier way to make as much money as possible. So the purpose of studying physics is to make as little money as possible. No, I'm joking. But so what's the purpose of studying physics? The purpose of studying physics is to understand nature, right? Ultimately, that's what we want to do. When everything is settled and done, we want to understand nature. You want to understand why the electron in a magnetic field spins at this rate. Okay, so Schwinger solved that problem. So we want to understand nature. And that's why we need quantum field theory. I like to talk about the intellectual completeness of different areas of physics. And I think this is important for students to realize this, for undergraduates. So for example, the Pauli exclusion principle and the spin statistics connection, which says that integer spin, particles integer spin is a boson, half integer spin is a fermion, and fermions obey Pauli exclusion principle. And there's a book by Duck and Sudarshan. He's actually German. I should not call him Duck. That's how Americans pronounce his name. It's probably Duke. There is no one fact in the physical world which has a greater impact on the way things are. This is an interesting book I recommend to students. They talk about how important the Pauli exclusion principle is. So from atoms to neutron stars to lasers, most of condensed matter physics, band structure, superconductivity, et cetera, they all depend on the exclusion principle and the spin statistics connection. But if you take a course in non-relativistic quantum mechanics, you can ask the professor, where does this rule come from? The professor will not be able to give you an answer. This is just a rule in non-relativistic quantum mechanics. Nobody told you this. You could have integer spin particle be fermions, or half integer be bosons. So quantum field theory can explain this, right? So this can be derived, and it's the famous spin statistics theorem. I think there's a great triumph of quantum field theory. So quantum field theory is more complete than quantum mechanics. So when I thought of the different areas of physics, which area is more intellectually complete, I would say quantum field theory is more intellectually complete. So there's some rule in some field that is then actually derived in other fields. So let me ask, how do you know? You can ask, I sometimes, by the way, all these famous physicists now are now dead. I cannot ask them these silly questions anymore, like Phil Anderson. You run into a famous condensed matter physicist. You're going to ask Anderson, how do you know that all the electrons in the world are identical? I mean, they could have been made in a factory somewhere in China, And And they're not identical. Some of them, of course, when you manufacture them, they could be slightly different. How do you know? And so on. So quantum field theory, we need quantum field theory to explain this. And the explanation, as Professor Toraba knows, is so elegantly simple, it has to be correct, right? That all electrons are just excitation in the same field. So of course they're identical because they're excitation in the same field. There's only one field. Okay. Now, I can also ask you, why is the electron charge exactly equal in magnitude to the proton charge? So in school, we learned the electron charge is -1, the proton charge is +1. Why are they exactly equal and opposite? Okay? So quantum electrodynamics in this sense of Feynman and Gell-Mann is less complete than grand unified theory. In grand unified theory, you can explain this. But in quantum electrodynamics, there is no explanation. You can ask Feynman this question. He will not be able to answer. Okay. Because in QED, you can put the electron to have charge -1 and the quarks to have any charge you want, and so on. So, but in grand unified theory, group theory requires the charges to be related. Now, why is, you can ask, at quantum field theories, why is space-time 3 + 1 dimensional? Then the quantum field theorists cannot answer this question. As I emphasized, you can write quantum field theory in any space-time dimension you like. So in this sense, it's less intellectually complete than string theory, right? Then string theory can tell us the dimension of space-time is fixed to be 10, okay? Now, whether or not you like the answer is a separate issue. Now, maybe you don't like the answer, maybe you like the answer, but it can tell you this dimension of space-time like quantum field theory cannot. So quantum field theory is less intellectually complete. Now, perhaps one of the deepest mystery of physics, is that the dynamical evolution in the quantum world is by this e to the -i(ht) over h bar, right? By this exponential with an I. And in statistical mechanics, there's a Boltzmann factor, e to the minus beta h. And the only difference is that there's I, there's no I. So there's imaginary time, so you can use this fact as, you can exploit this fact, it can be applied. So for example, you can calculate Hawking temperature of a black hole almost in half a page using this connection with quantum field theory, because the inverse temperature and imaginary time are related. So is this just a coincidence or a deeper fact? I've asked many physicists about this before they died. I mean, for example, Nambu told me that he thinks there's something deeper. But then the other physicists I asked, they said this is trivial. This is just a triviality, coincidence, because we all learned this in school. Entropy is logarithmic, and it's the logarithm that gives you this exponential. So I think this is an important question for some young person to think about. So then I already said this in some sense, the partition function, therefore, in statistical mechanics and condensed matter physics, can be represented as a Euclidean field theory, in contrast to Minkowskian field theory, because time is them. Imaginary, many other problems in physics can be represented as field theories. So, there are two great marriages in physics. In the 20th century, we have married quantum physics and special relativity, and we get quantum field theory. That was the subject of this talk. But Einstein had two daughters, special relativity and general relativity. And in the late 20th century and early 21st century, not finished yet, we want to marry quantum physics to general relativity. And we don't know what this would lead to. Maybe string theory or perhaps something else. We don't know. So, thank you very much.
much, Tony, for the talk. Bueno, ¿preguntas?
Good afternoon. Thank you very much for your thought-provoking talk. I'm a condensed matter physicist, and I would like to know your thoughts on Phil Anderson's ideas on reductionism and the emergent phenomena, because your approach was quite reductionist.
Yes.
And Phil Anderson had criticisms to that. So what are your ideas?
I talked about this at great length in a book that I'm writing, and I think there is no contradiction. I know him quite well, and he certainly, I think most people realize that physics should move in two different directions. I think there's no tension at all. The tension is created by people, and more by funding agencies, people fighting over funds. You can certainly there's nobody who claims that physics should be completely reductionistic.
Well, thank you. I was curious about the tiger in the cover of the book. Maybe I missed the explanation. Thank you.
Well, thank you for asking. The tiger is the burning tiger is based on a poem, a famous poem by William Blake. So it's extremely well known in English-speaking countries. William Blake is an 18th century British sort of mystical tendency, and so it's about. Perhaps I should show the. The burning tiger was the one way he tried to express why there's symmetry in the universe and who put the symmetry there. That he asked these questions. So perhaps I could use your question. I could use your question to try to entice you, to encourage you to read my book.
More questions? Okay, well, we thank Tony again.